Welcome to week 2 lecture 3. In the previous lecture we have seen the construction of block ciphers, particularly substitution permutation network and Feastel ciphers. We have also encountered something called an S box or substitution box, where a block of bits are accepted as input and which is substituted to another block of bits not necessarily of the same length. We will have a closer look at substitution boxes or S boxes in this lecture, but before we do that we have to have some idea of Boolean functions. So, we start with Boolean functions. Again, to start with Boolean functions we have to know Boolean algebras or a particular type of vector space on which Boolean functions are defined. So, here we start from something very simple. We have a set containing just 0 and 1, and on this set we define operations. The first operation is like addition, it is called XOR or addition modulo 2, and the rules are given here, and the second operation which we denote by a dot, but when we are writing the formulas we do not write a dot, we just do not write anything, just write two symbols side by side to denote this operation. This can be called AND or multiplication modulo 2, and the rules are given here. The salient point is that of addition modulo 2, to recall again, is that 1 plus 1 gives me 0, and salient point about this is that 1 into 1 gives me 1 and rest of the entries are zeros. We say that if we have this set 0 1 and attach to it the operations XOR or addition modulo 2 and AND, or addition modulo multiplication modulo 2, addition mod 2 over here, and this one is called AND or multiplication mod 2, then we have an algebraic structure which we call GF2. It is also sometimes called the prime field of characteristic 2. We are not going into details about prime fields, why it is called a prime fields and what are extension fields and all that, but what we do now is to take Cartesian product of GF2 n times to obtain GF2 to the power n, which is essentially all binary sequences of length n. Once we have this, then we define functions from GF2 to the power n to GF2, and these functions are called Boolean functions. So, I take GF2 to the power n and define functions from GF2 to the power n to GF2, and these are called Boolean functions. Now, as an example, we see a Boolean function here. Now, if you look at this, you will see that I have listed down the elements of GF2 to the power 3 in a particular order, and this order is exactly the order in which the natural numbers corresponding to these bit streams, if I consider the right hand side to be the least significant bit and left hand side to be the most significant bit, this is the order in which the numbers come. I mean, if we are changing these binary strings to natural numbers. So, it starts from 0 0 0, 0 0 1, 0 1 0 and so on, and ends in 1 1 1, and I can take any string over here of zeros and 1, and that gives me a function. In this particular case I have taken a string 0 0 0 1 and 1 1 1 0. Okay, this is a Boolean function, and this particular representation of a Boolean function is called the truth table representation of a Boolean function, and this is called the truth table. We move forward to see another way of writing a truth table. If I assume that the ordering in which the elements of the domain comes is fixed, and this is the order, then I can just write the string over here, which is the right hand side of this table. We can write one after another, and we can say this is my truth table, and I can always get the function from it. In general, if we have let us say n equal to 3, I can write in general a truth table like this. I have written here n, please read this as 3. So, well, you can read this as gf2 to the power n, but I am doing this for gf2 to the power 3. If it is any n, then we will have a string of zeros starting from here of length n, and then I will write 1 and all 0, then I will write 1 0 and all 0, then 1 1 and all 0, and we know how to proceed. You may try this for n equal to 4, n equal to 5, etc., and see the ordering. Now we have a concept of algebraic normal form. What we can do is that we can associate variables to the input bits. We have already done that. Please see that this is the leftmost input bit, and I associate x1 to it, then after that I associate x2 to it, and then the next to the last one I associate x3. So, if I come here, I can basically write an algebraic expression of this type, and that is called a algebraic normal form of the Boolean function. The algebraic normal form of Boolean function is unique. I am again not going into the proofs of that, but we more or less understand algebraic normal form. So, if we come here, we come back to the same function, then we see that if we had evaluated an algebraic expression like this, then if I take the input f00, then of course it is 0. Then if I take the input f001, then of course here x1 is 1 and x3 is 0. So, 0 plus 1 times 0, so it gives me 0, and we come down and let us say if I take x100, we see that this is the input bit corresponding to x3, this is corresponds to x2, and this corresponds to 1. Therefore, we will get 1 plus 0 into 0, so it is 1. So, in that way we can evaluate all the values, and I definitely would advise you to do that, and you will see that you are getting the same sequence as this. So, this Boolean function has the algebraic normal form x3 XOR x1 x2. Now, there is of course a question how to derive algebraic normal form from truth table and truth table to algebraic normal form. I will set this up in the assignment for you to check literature to find out the rule, and I will discuss that rule when I discuss the assignment problems. So, let us go forward. Now, we see that essentially if we fix the ordering of the domain elements, then the only thing that matters is the sequence in which the functional values appear, and suppose we have got two functions, then we can talk about distances between Boolean functions, and that is that has got a name, it is a famous distance, it is called Hamming distance. Hamming distance, and this distance is exactly the count of the number of places the functions, the two functions do not match. So, the Hamming distance of f and g is 4 here, because there are 4 places where the functions do not match. If we check in this table, we see that in the first place the function do not match, and the third place the functions do not match, the fourth place the functions do not match, they match here. So, I have already counted 3, and there is a last place here, the sixth place the functions do not match, and so therefore, the Hamming distance is 4. So, next we have affine functions. Now, we have talked about algebraic normal form, and let us go back. If you look at algebraic normal form in general, you will see that there are many terms over here. Particularly, there is a constant term without any x, and there are terms with only single x, single xi, so to say, and there are terms with a product of 2 xi's, and then ultimately a term at the end which contains a product of all the xi's. But if we consider a function whose algebraic normal form contains a constant term here and only the terms which have single variable, then that function is called an affine function, and the set of affine functions is denoted by the symbol script a sub n, and affine functions, the set of affine functions has a subset which is also very famous. This subset is called the set of linear functions and denoted by script L sub n. So, a function is linear if a0 is 0. So, if the constant term is 0, then the function is called linear. Now, we come to an idea to which we were driving. So, we come to an idea which I had in mind, and I was driving at it. So, this is the idea of non-linearity of a Boolean function. So, suppose we have a Boolean function, we think of it as a string of length 2 to the power n, and we are considering the set of all affine functions, and we are considering the Hamming distances of each affine function to that particular Boolean function. And if we find the least Hamming distance, then that least value is called the nonlinearity of the function. So, I have to consider the set of all affine functions and vary phi over the set of all affine functions and keep f fixed, and nonlinearity of f is a minimum of all df phi. This needs an example. So, let us do that for n equal to 2. So, I am taking n equal to 2 and my values are 0 0 0 1 1 0 1 1, these are my domain points, and my function is 0 0 0 1. This is my function, and I will now list down all the affine functions, I have got one special function which is all 0. So, I write all 0 over here, and then I have got the function x1 and x2. So, x1 is 0 1 0 1 and x2 is 0 0 1 1, and I take x1 XOR x2, this is 0 1 1 0, and then I take complement of all these functions. So, I have got 1, that is all 1, then this is 1 XOR x1. So, it is complement of this. So, 1 0 1 0, and then I have 1 XOR x2. So, this is 1 1 0 0, and this is 1 XOR x1 XOR x2, this is 1 0 0 1. Now, I have to compare this function with all these functions and check the distance. Here the distance is 1 because it differs only in one place, and now see that, for example, here the distance is again 1. Okay. Then here the distance is again 1, but here please see the distance is 1 2 3 4. So, distance is 4. Here the distance is 3, here the distance is, it differs over here, here and here. So, distance is 3, here again the distance should be 3, yes, and here the distance is 1. So, we see that no, yeah, the distance is 1, and let us say here, yes, the distance is, no, this distance is not 4, I mean, like it is wrong here, this is same, and here it is different. So, it is 3. So, there is a pattern like this, and this is what I am doing, and these are all the, here the distance is 1. So, these are all the affine functions. So, if we try to compute the nonlinearity, nonlinearity is the minimum distance as this. So, nonlinearity of the function f is going to be 1. Now, the question is, how do we connect Boolean functions to S boxes? The answer is in this slide. Suppose I have got an n by m S box. So, that S box is taking n bit input and giving me m bit output. So, I can consider that S box as a function from gf2 to the power n to gf2 to the power m, and then I can take, so to say, each coordinate functions. Let me draw it over here. I have got n bit input and some n bits output. So, what I am doing, I am taking all of these things and concentrating on this. I call it f1 and then I call it f2 and so on. That is what I have written here. So, fx can be split up into a sequence of Boolean functions f1 up to fm. So, here for example, I have got this input and I will push it, I will consider only this output and call this a Boolean function f1, then take this input and consider here this Boolean function f2 and up to fm. So, therefore, the function f, suppose this is a function f which is my S box, is a sequence of Boolean functions like this. Now, these functions are called coordinate functions of f. Fi's are coordinate functions. Now, what one would presume that if we have to have a good Boolean function, then good S box, then its coordinate functions must be good, in the sense that that should be cryptographically good properties, like possibly the coordinate functions should have good nonlinearity, which will make it difficult to approximate by linear functions. But it is not enough to check only the coordinate functions. We have to do a bit more over here. We have to check the so called component functions. So, what we have to do is basically to take all the linear combinations of the coordinate functions, which is called component functions, and which I have written over here. So, I take a vector in GF2 to the power m and call it V, and then I am just taking a linear combination by multiplying V1 with F1 and XORing with V2 with F2 and so on. So, if I have got just a 3, let us say if I have got a just 3 coordinate functions F1, F2 and F3, then my component functions will be of course the 0 function and the function F1, F2 and F3, which are the coordinate functions, and then I will have F1 XOR F2, F1 XOR F3 and F1 F2 XOR F3, and finally F1 XOR F2 XOR F3. I will have that, and that is what I have written over here, and I would request you to check that after the lecture. So, what we know is that if we have to have a good S box from the point of view of cryptography, then the coordinate functions are not enough. The component functions have to be strong, and by being strong I mean they should have good cryptographic properties. Now, what are these properties is a very difficult and a difficult question, and all the properties are not yet known. We will be discussing some of the properties in the next lecture. Probably we will be discussing only one property, that is nonlinearity, in the next lecture, and try to understand how nonlinearity controls the cryptographic vulnerability. Now, there is one example that we can check. I give you one S box. So, it is a 3 by 2 S box. It is completely listed over here, and I will ask you to find all the component functions. That is an exercise, and we have come to the end of today's lecture. To sum up, we have studied S boxes, we have studied coordinate functions, we have studied component functions, and most importantly we have introduced the idea of nonlinearity. That is all for today. Thank you.